Now, continuing our discussion on some of the physical properties, we want to talk a little bit about intermolecular attractions. And so these are temporary attractions that are going to be between two atoms or two molecules or two ions, and they are going to affect your physical properties, such as your boiling point, melting point, different things like that. So let's learn a little bit about intermolecular attractions. These intermolecular attractions are attractive forces between molecules. These are not chemical bonds. It's not a permanent sharing of electrons or anything like that. What is happening is that the two atoms or the two molecules are close to one another and they have this slight attraction to one another. Now, these attractions can occur due to different ideas or different reasons why. And based on those reasons, we can actually divide intermolecular attractions into three different areas. The first type we want to talk about are called dispersion forces. Now, depending on what textbook you use, these may also be called London forces, and some textbooks will call them van der Waals. That's named after a guy, of course. But van der Waals can also be used as like an overall, all of the intermolecular attractions are examples of van der Waals. So be careful of the van der Waals. That one depends on the book. That was an LS there at the end. Most likely you'll hear dispersion or London forces for this one. These are really weak attractive forces due to proximity. So just because two atoms or molecules are close to one another, there's some London forces or some dispersion forces, these weak intermolecular attractions between them. Now, this will increase with an increase in size. And now I want to clarify this. This is of molecules. So if you have really big molecules, you're going to have more of these dispersion forces than if they're really small. So when we get to looking at hydrocarbons, these dispersion forces become very, very important because we have really, 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 really large molecules. And every molecule has dispersion forces. It doesn't matter if it's a polar molecule where there's an unequal sharing or a nonpolar where the electrons are shared equal. Every single molecule has the ability to have these dispersion forces. I'm going to show you a picture of this. I think it's on the next slide. But let's go ahead and talk about the next two really quick. The next one's called a dipole-dipole. Dipole-dipole is going to deal with polar molecules. So polar, if you remember, that means that there is an unequal sharing of electrons. Unequal sharing of electrons. Now, within this idea of dipole-dipole, again, we're going to see this a little bit more on a future slide. A special type of dipole-dipole is called hydrogen bonding. Now, hydrogen bonding can only occur between certain elements. You're going to have hydrogen on one molecule, hydrogen on one, so it's called hydrogen bonding. And on another molecule, you're going to have nitrogen, oxygen, or fluorine. Now, if you would, look at your periodic table really quick and see where nitrogen, oxygen, and fluorine are located. What you'll find is that they're all three in the upper right-hand corner. They're all in the same period. They're in period 2. They're going to be really small elements, small atoms that are very electronegative. Oh yeah, we're going to talk about that electronegativity. And because of that, they like to try to have this temporary attraction to a hydrogen in another molecule. So again, we're going to look at all three of these in a little more detail. On this slide, we really want to focus on our dipole-dipole, and then also we're going to look at some hydrogen bonds. This particular slide is going to look specifically as water as an example of both of those. So water, if we were to draw its Lewis structure, We've got oxygen with 2 hydrogens. There's 2 lone electrons. And between the oxygen and the hydrogen, that's considered to be a polar bond because it turns out that the oxygen wants the electrons a lot more than the hydrogen does. So what we could do is we could actually draw an arrow that says the electrons want to go towards the oxygen. They don't like the hydrogen quite as much. And the other bonds, same exact thing's going to happen. Those electrons that are being shared between the hydrogen and oxygen spend more time around the oxygen than they do the hydrogen. Now, the arrows are one way that we can indicate that we have a partial positive and a partial negative charge. Notice I said partial. This is not a true charge. It's not ionic where we're transferring electrons. They're still sharing them. It's just not quite equal. Okay, here's your bad example. Do you have a sibling? Are they older or younger? In general, in a family, who gets to drive the car more? The older sibling or the younger sibling? Well, I know with myself, now it could be because there's a big gap in between me and my brother. But even with my kids, the older sibling gets to drive more. They share, it's just an unequal sharing. It's just the way it is. The older sibling drives more. Is your experience the same? So a polar bond is kind of like that, where they're still sharing. They're sharing the electrons in that bond, but one of the atoms, one of the elements, likes the electrons more. So we're still going to show a dash to show that there's an electron, but we could draw the little arrows on top, or we could say that the oxygen is partially negative and the hydrogens are partially positive. Now, isn't that kind of a really weird little symbol I drew there? This is a Greek letter. It's a lowercase Greek letter. Did you know Greek letters have both upper and lowercase? The uppercase Greek letter you're probably a little more familiar with. Looks like that. Okay, do you know what that is? That one is delta, the little triangle. And what does delta mean? Delta is change in. So the big delta is change in, the little delta is a partial change. So we have a partial negative and we have a partial positive. Well, now with this case with water, we said that the oxygen was partially negative, the hydrogens are partially positive. Well, if the oxygen of one molecule comes close to the hydrogen of a different molecule, it forms this little temporary attraction. That's a hydrogen bond. Now, hydrogen bonds are examples of dipole-dipole. Now, they call them dipole-dipole. It's just the name that they've always used. But if you think of what a dipole is, well, usually you use magnets to think about that. And if you've ever played with magnets, you know that a magnet has a north and a south end. They have 2 poles, just like the Earth has 2 poles. That's why it's called a dipole, because there's 2 parts to it within that same molecule or within that same Earth or the same magnet or whatever you're looking at. So partial positive, partial negative, a north and a south. So what happens here is if we can align, well, let's go back to that magnet example. Hopefully you've played with magnets. They're fun to play with. If you turn a magnet just so, if you have 2 magnets, they're attracted to one another. But if you take one of the magnets and you flip it over, they'll start to repel one another. Well, that has to do with those poles, and atoms and molecules will do something similar. So if we have a partial negative end on one molecule and a partial positive end on another molecule, they have this temporary attraction between them. Again, it's not as strong as a regular covalent bond. It can be up to like 5 to 10% the strength of a covalent bond, so it's much less. But it's still there. And if there's enough of them, they can have an effect on the properties of that substance. Now, if we happen to be working with hydrogen on one element and nitrogen, oxygen, or fluorine on another, That is a special case of a dipole-dipole called hydrogen bonding. And that's actually what we're seeing in this example. So just to recap, that little dotted line, it's not a covalent bond, it's a temporary attraction, a temporary what we call intermolecular attraction or intermolecular force between those two molecules. But what happens if your molecule isn't polar? What happens if the atoms are shared equally between the two atoms? Now that's going to happen with what we call a non-polar compound, non-polar. So here they're sharing equally. If we go back to our example of siblings driving, this is going to be the example of twins that share everything equally. Now I know twins do not share things equally. I had a set of twins growing up that were good friends of mine. They did not share things equally, but they became a lot closer than other brothers or other siblings would come. So nonpolar means that they have, again, they share the electrons equally between the two atoms. Now these are going to be things that have very, very similar electronegativities. Carbon and hydrogen will do this. Now, because sometimes it's hard to figure out whether or not their electronegativities are similar or not, normally we show this with the same element. So between two carbon atoms or between two hydrogen atoms, between two fluorine atoms. But if it's carbon and hydrogen, those also have very, very similar electronegativities. So this top one right here, let's look at this and let's see if we can figure this out. A little bit of review in here. Now, here we have some colors representing different elements. What does the black color represent? It represents, yes, you are correct, carbon. And the white represents, that's right, that's our hydrogen. So this particular substance has three carbon atoms. Do you remember the prefix for 3 carbon atoms? That particular molecule is called propane. The ane indicating that we have only single bonds. The prop indicating that there are 3 carbon atoms. So here we don't have partial positives or partial negatives. Everything is being shared equally, but it turns out that occasionally there's an overall shift. All the electrons tend to go to one side than the other. Maybe they move too fast, who knows? And so we can have these really, really quick, instantaneous, momentary, temporary attractions, transient partial charges that are going to occur. That's what we call those dispersion forces or those London forces. And the longer this molecule is, the more likely these little temporary anomalies are going to occur to have these London forces or dispersion forces. Along with this idea of changing phases, we can look to see how this changing of phases affects the rest of your sample. So on top, we have a beaker that's filled with a liquid. And we can see the liquids on the bottom because the molecules are pretty close to one another. And then above the surface, we have some molecules that have evaporated. And those that have evaporated have a lot more distance around them, a lot more empty space. We can see the vectors of the little molecules right behind them, showing that they're moving super, super fast. So we have a couple of different ideas going on here. So remember, in the liquid, each of those molecules has its own kinetic energy. And kinetic energy is just the energy of motion. Some are moving really fast, some are moving a lot slower. And if one of those that's moving really fast gets to be on the surface, if it has enough energy, it can actually evaporate to become a gas molecule. So that's our idea of evaporation. Okay, now we're going to throw out another concept here, and we're going to relate the two. The other concept I want to talk about is temperature. Now, we defined temperature earlier today. We said that temperature is the average kinetic energy of molecules. So let's write this down. Temperature is the average kinetic energy. So remember, each of those molecules has its own kinetic energy. And if I wanted to, just like I can look at the class scores, I could look at the overall average of all those kinetic energies. But what would happen if a bunch of those that have the really, really high kinetic energies, what if they left the sample? What if they evaporated? Well, if they evaporated, what I'd be left with are molecules that have overall lower kinetic energies. And if I was to take an average of that new group, their overall average would be lower. And so it turns out their temperature is going to be lower. Now, our body actually uses this idea, and it uses it to where we can self-control, or we can help control our body temperature. And we're going to use sweating as an example of that. So if you're working out, if your body starts to get overheated, the body starts producing sweat. And what'll happen is that, so we'll have this thin layer of that water, or really dilute inorganic acids on the surface of our body. And then our body is going to use some of its energy to heat up those molecules to evaporate them. Well, when they do that, the molecules that are left behind have a lower overall kinetic energy. So that can actually be used to help cool our body. Isn't our body just amazing that it can do this itself? We don't even have to control it. We don't even have to think about it. It just happens. This slide is here just as a reference. I wouldn't expect you to memorize all these. Water you have to memorize, but not necessarily the others. This is looking at common melting points and common boiling points for some different substances. For example, oxygen, it is going to melt at negative 218 degrees C, meaning if we wanted to freeze oxygen, if we wanted solid oxygen, we would actually have to cool it to negative 218 degrees C, and it boils at a negative 183 degrees C. So we'd have to cool oxygen down to a negative 183 before we'd even get to see it as a liquid. Now, just as a reference, what is the common room temperature in degrees C? I know I'm not really great with degrees C, but we should be a lot better than what we are. We know that water freezes at 0, it boils at 100 degrees C, and 20 is about regular room temperature. So if we go down and we look at these, we can actually predict what phase different substances will be in at room temperature. So look down at, let's look at ethanol. So ethanol, and ethanol is just your drinking alcohol. It is going to melt at negative 117 degrees C. So that is, you'd have to drop it to that temperature to get it to freeze, because it turns out the melting point and the freezing point are actually the same temperature. It just depends on which way you're going of a pure substance. So have you ever tried to take a really high content alcohol, or heard about this, because I bet most of you aren't quite legal drinking age yet. Maybe you've seen someone do this before, where if you take something like Everclear, which has a really, really high alcohol content, you can stick it in the freezer and it won't actually freeze. That's the reason why. Now, if you have something that's really dilute or not as concentrated, there's a lot more water in it, you will start to see some of those start to freeze, but the temperatures will be lower. Not saying you should try that, by the way. No. So ethanol freezes at negative 117 and it boils at 78. So at room temperature, which again is about 20 degrees C, it's going to be in a liquid state. Now it's fairly easy to boil ethanol off of a substance. So if you've ever added like cooking sherry or a brandy or a wine to a food as you're cooking it, that alcohol part is actually going to boil right off, but it's going to leave behind some of the flavoring that we want. If you were in class, we'd actually do a lab where we would look at the boiling point of ethanol. Acetone is the same way. At room temperature, it's going to be a liquid because it's in between the melting and boiling temperatures. Then if we get up to something, say sucrose melts at 185 degrees C. That's well above room temperature. That means that sucrose is going to be a solid at room temperature. So kind of have an idea of being able to look at these different temperatures. In what phase is something going to be in?